Nima Arkani-Hamed, and he's talking about quantum mechanics and space-time in the 21st century.
Back in Bangalore, I was here, I think, around 2.5 years ago, and I'd like to join everyone else, in congratulating Spenta et al. On the spectacular job that you've done here. The title for this lecture is, I think, actually the same as the title of the lectures I gave here a number of years ago. The content will be a little different. Of course, it's not a small subject. So here's an outline of what I want to talk about. I want to talk about two things. Well, first, that it's a large subject, but it befits the celebration of a new center where you want to think about not just all the effort that's gone into the past 5-10 years, or what might happen in 5 years from now, but what the fruits of the labors here and elsewhere might look like on a longer time scale. So that's what I'd like to do today. First, I'm going to start with a brief review of the two experimental frontiers in fundamental physics, both at very short and very long distances. Talk briefly about the central dramas, theoretical dramas of the 21st century, which are ultimately a deeper understanding of the origin of space-time and perhaps a deeper origin of quantum mechanics itself. There's a second set of questions I won't have a chance to talk about at all, about why the universe is big. And then I'll engage in some absolute speculation, which I've divided into crazy speculation and really crazy speculation. So the first set of things which I'll briefly talk about is the thought that what we'll come to see is that space-time and quantum mechanics will actually be seen to emerge hand in hand together from more primitive building blocks. And the really wild speculation is that towards the end of the 21st century, or maybe in the 23rd century, or sometime, we'll eventually come to see that cosmology and number theory are deeply related to each other. So first, some experimental frontiers. So we've been going to very high energies, short distances of very high energies for around really 100 years, starting from Rutherford. And of course, gloriously, the LHC in the last run discovered the Higgs particle. It's started back up again right now. So that's the first thing to talk about, and certainly the next five years is an absolutely critical time for the operation of the LHC. So here's a sort of canonical picture that you've all seen. We're colliding. We have energies, 14,000 times the mc squared of the proton. Velocity is 0.9999979 times the speed of light, and probing distances that are 1,000 times smaller than the atomic nucleus, which is in turn 1,000,000 times smaller than the atom. So that's what's going on right now. But given that these machines take the better part of a generation to conceive, plan, and build, if we're going to have a 20, 30-year future beyond the LHC, the time to start thinking about what that future is going to be is now. And fortunately, that's happening in a serious way around the world. Unfortunately for me, it's not happening in my own country, but fortunately for the world, it's happening somewhere. Both CERN and China are seriously considering the possibility of ultimately taking one other big step forward in energy, roughly 8 times higher than the energy of the LHC, to go to 100 TeV proton-proton collider. The cost of this is 10 billion in your favorite units of currency. But that's certainly not deterring the Chinese. It might be more of a problem elsewhere in the world. But anyway, the idea is that it's around a 100-kilometer tunnel. The energy ultimately around 10 times higher than that of the LHC, and that it could start being it could start getting going on the 20-year time scale and the mid-30s time scale, actually doing physics. So if this actually moves forward, this is what the 20 to 40-year future of the field would look like. And to show signs of seriousness, this is kind of the plot that makes particle physicists very happy, is a map of the world with rings on it. Okay, and so here's a map of the world around Geneva. There's the LHC, and there's the putative 80 to 100-kilometer ring. And there is a map of the world. It's around 300 kilometers northeast of Beijing, with a 50-kilometer and 100-kilometer ring. You see there's easily room here for 150 kilometers, but let's not push our luck. Okay, so that's what's being talked about on the frontier of very short distances, very high energies. And now, just something to keep in mind is that the LHC is a glorious machine, but there was a machine that was better than the LHC, which was called the Superconducting Collider. That's a machine that would have guaranteed to completely explore the physics of the TeV scale. As David has remarked a number of times, it's a very good comment. If you want to understand physics at an energy scale E, you don't go just to around the energy scale E. You go to energy 10E, so you see everything which is going on, so you're sure you're not getting, you're not just missing things, or you're not being messed up by surface effects. The LHC people anticipated for a long time would discover things like supersymmetry. Certainly there's a 30-year version of supersymmetry that's been anticipated for around 30 years. That's funny that the LHC is not seeing yet. Perhaps we're about to see it this year, or in the next few years. But if we don't see it, it doesn't mean that it's not there. It could be just slightly out of reach. It could be a slightly different character than the one that people had been anticipating. Many theorists had come up with other versions of these ideas which could just be missed by the LHC, but simply cannot be missed by the next machine. And this is, you don't need to look at any details here. Unfortunately, you can't see, it's a little grainy. But the beautiful thing about physics at 100 TeV collider is that for the first time, all of the units and all of these axes are comfortably TeV. So you can probe 10, 15, 20 TeV gluinos and produce them at a 100 TeV collider. If you don't discover superpartners at 100 TeV collider, the usual picture of supersymmetry for solving the hierarchy problem, for example, is just wrong. And you can just say it's just wrong, period, full stop. With the LHC, the ones that were popular are wrong, but you're left with an uneasy feeling about what it tells you. Anyway, so that's, I think, something worth working very hard to turn into a reality. And fortunately, there are people around the world who have the vision to pursue it. In the other direction, we have the physics at the very, very large scales. And here, of course, the biggest excitement in cosmology for the last 20 years has been more and more precise measurements of the cosmic microwave background, starting from the COBE, then to the WMAP satellite, and most recently the Planck collaboration. And of course, at 0th order, the cosmic microwave background, we just had a wonderful conference at Princeton last week celebrating the 50th anniversary of the discovery of the CMB. It's amazing what's happened on the 50-year timescale. You just go from seeing, white noise in the sky to getting these incredible plots of very, very detailed, amazing measurements, not just of the temperature, but of the temperature, subtle temperature differences of around a part in 100,000 from place to place to place in the sky. These tiny 1 part in 100,000 temperature differentials ultimately coalesce under the force of gravity to turn into all the structure, you and I and everything else that we see in the world today. Now, we have a beautiful theoretical framework that lets us explain many of these features. That's the idea that the universe started with a period of inflation before the hot Big Bang. And while the last 20 years of cosmology have been really all about measuring the CMB and the actual, if you like, the two-point function, the next 30 years of cosmology are really going to be about looking to see if there's any patterns. Right now it looks like Gaussian noise with an amplitude of around a part in 100,000. The next big program in experimental cosmology is going to be to look for patterns, to look for non-Gaussianities. And that's because what that's doing is a very precise analog in cosmology of what we do in doing experiments in particle physics. It's something that you could rightfully call cosmological collider physics. What we do in particle physics is before we do anything fancy, we first have to see who are the stable particles in the world. So the stable particles in the world are electrons and protons, for example. And we determine who the stable particles are by measuring two-point functions. Okay? So what are the two-point functions that survive at long times? After we decide who's stable, however, those properties, the properties of those two-point functions are basically controlled by symmetries, Lorentz symmetry and translational invariance. After we find who the particles are, all the dynamics comes from colliding them, banging them into each other, and looking for the presence of new particles or interactions from patterns in the cross-sections that you get when you bang them into each other. So, for example, at a proton-proton collider, ultimately the quarks on the inside are banging into each other. The coupling constant at short distances is small. Something happens, so particles come back out. Eventually the coupling becomes large at very big distances. These things turn into hadrons, and what we measure experimentally are large jets of these particles coming out. The story is almost identical in cosmology. The first thing you have to do is figure out who are the stable particles. In this case, it's by measuring the 2-point functions of the density fluctuations or the temperature fluctuations in the CMB. Just as over here, the 2-point functions are basically completely determined by symmetries. In this case, it's not the Poincare symmetry, but it's the approximate de Sitter symmetry of the underlying inflationary epoch. And just as the previous case, all the interesting information about dynamics comes from looking at how these infotons interact with each other. So now you're looking for patterns in the non-Gaussianities. A very similar story. We can have some interactions between these guys and other particles that were present during inflation. The interactions here at short distances in the early universe are incredibly weak. The coupling is around 10 to the minus 5. But as here, as you go to very long distances, gravity eventually becomes strong. And the analog of hadrons in particle physics are galaxies in cosmology. Okay? And the analog of studying jets is doing galaxy surveys and looking at average properties of galaxies on large scales. So there's an enormous amount of information which is sitting there in the pattern of the potential non-Gaussianities that we can see. And we can use that pattern, just like we do in particle physics. We look for peaks in the cross-sections to determine whether new particles were present or not, and even look at angular dependencies to learn about spin. We can do exactly the same things by studying non-Gaussianities. If I look at the density perturbations at 3 points in the sky, I take the product of the density perturbation here times there, and I average over all the triangles in the sky with the same shape. I get some function of the shape of the triangle, and that function in momentum space has some interesting patterns in it. If there's a new massive particle that's being exchanged by the infotons, for example, you can show that there's an oscillatory pattern in this 3-point function, and the frequency of that oscillation, it's an oscillation in log k, and the frequency tells you the mass, and the angular dependence tells you the spin, exactly like we do in particle physics. This information is out there. The energy scale during inflation could be as high as 10 to the 14 GeV, just 2 orders of magnitude beneath the unification scale, 4 orders of magnitude beneath the Planck scale. These are energies we will never access on Earth with a big accelerator. But the information is written on the sky in principle, if these particles are out there. And while the amount of data in the cosmic microwave background itself is too small, just the statistical fluctuations in the data is larger than you'd expect to be able to dig out these small signals. We're in a new era of experimental cosmology in the next 20 or 30 years. This is a picture of what part of the universe we've actually looked at and seen. The little red is what we see in our immediate neighborhood. This tiny little sliver out at the edge is what we see from the cosmic microwave background, and everything else is empty. We don't know anything about it. Okay? The next 20 or 30 years of experimental cosmology is all about starting to fill this picture in and get a whole volume's worth of universe to uncover. So these experiments will, in principle, if you just ask, is there enough data such that the ultimate statistical limits from random fluctuations aren't a limiting factor? Is there enough data to be able to see the effects that I'm talking about? The answer is definitely yes. There's a factor of 100 million more modes that we can get in the whole volume of the universe, and we've seen so far in all of our cosmological measurements of these density perturbations. And this is a big piece of the experimental program for fundamental cosmology on the 20 to 40 year time scale. So in particle physics, we have to build a giant new collider. And in cosmology, we have to learn to turn the cosmos into a giant collider and figure out how we extract the information, which is written out there to learn something about physics at these potentially incredibly high energy scales. Okay, so that's the brief overview of the experimental frontiers, and I want to spend a little bit of time talking about the theoretical frontiers. So there are two dramas, as I mentioned before. The two dramas are that we suspect space-time is doomed, and perhaps because of very subtle, deep questions in making sense of not just cosmology, but cosmology in accelerating universes like ours, we may be running into limitations of quantum mechanics, as well as this question of why the universe is macroscopic that I won't have a chance to get to. Now, there are many very simple reasons theorists have long suspected that there is something suspect with the notion of space-time. If you try to use a magnifying glass to probe little tiny regions of space and time, you have to put more and more energy into a smaller and smaller region of space by the uncertainty principle in order to do that, but at some point you put so much energy into such a small region that you collapse it into a black hole, and it becomes impossible to probe what's going on there anymore. And if you get frustrated, you build an even higher energy accelerator, a more powerful microscope, you make an even larger black hole. So there's no way of operationally measuring space and time distances shorter than the famous Planck length and Planck time and so on. Yet another aspect of the problem is that if we consider a simple standard process like the collision of electrons, there's a piece that involves exchanging a virtual graviton, and that part of the probability amplitude scales like g Newton times the square of the center of mass energy of the collision, just by dimensional analysis. And while this is tiny when the energies are small compared to the Planck scale, this amplitude becomes bigger than 1 when the energy becomes large compared to the Planck scale, and so that doesn't make any sense. The amplitudes probabilities can't get bigger than 1. So that tells us that this formula that we get, standard formulas, has to be replaced by something else when the energies become high. Now, that's a good place to start, actually, because there's many, many things that quantum gravity's got to do. But this is one thing that it has to do. It has to give you an answer to the question, what happens when you scatter particles into each other and see what comes out? We can even do it with gravitons themselves. Let's say scatter 2 gravitons in, 2 gravitons out, and you don't need to pay any attention to the details of the formula. You just have to see there's a g Newton, and all the rest of these factors. I'm just writing it down just so you see how super concrete it is. There's a definite answer that you get from the lowest approximation in just our standard theory of gravity. But this has the feature, as we alluded to before, that the amplitude becomes very large as the energy becomes large. Okay? So it can't be right. This formula can't be right. So a first challenge is, can you fix this formula? This is a challenge for a theorist. Can you fix this formula? Maybe by writing down some factor here, which keeps the amplitude small, that turns, the factor becomes 1 when the energies are small, but somehow it becomes very small as the energies become large, such that the full amplitude never becomes large. Okay? Now, this is the sort of thing where you look at it first and just make a correct technical point, we can make an approximation to imagine that the underlying physics, whatever it is weakly coupled. That assumption turns into something very concrete about this function here, that in first order of approximation we can assume that it only has poles. And it doesn't have more complicated analytic structure than having poles. So we need to have a function that only has poles, and say, look, this is easy as cake, right? S, T, and U are just some measure of the energies. So I'll just write down something like 1 over 1 minus S, 1 over 1 minus T, 1 over 1 minus U, something idiot like that. And it's going to make the amplitude small at high energies. Everything is fine, I'm done, okay? You see, not only am I done, it's trivial. It's so trivial, non-predictive. Unless we can do experiments at the Planck scale, who cares? You can come up with 15 million different guesses as to what's going on, okay? However, we have to do more than that. We have to make sure that this formula is consistent with the idea that amplitudes add up, that the probabilities add up to 1. And that tells you something very specific, that on the poles, if we have poles here, that on the poles, the residue on the pole has to be positive in a specific sense of the word. Really, very precisely, it has to be expressible as a sum over generalized Chebyshev polynomials with positive coefficients. The positivity is where the positivity of probability comes in. Then if you try that with that first idiot example, you find it isn't. They're negative. Some of them are negative. They say, okay, then you'll try another one. Okay? You try 2, 3, 4, 10 examples. Always there's something negative. You prove that if you have any ratio of polynomials that you put in S, T, and U, upstairs and downstairs, all the time there's something negative. So this is typically what happens in the life of a theorist. You start by thinking a problem is easy, and then you quickly convince yourself that it's impossible. Okay? But then something amazing happens. Someone comes along with that formula. Okay? Say? Now, given that nothing else worked, to say, oh, you pulled some other formula out of your ass, I don't care, right? So there it is. But now you check, you sit on the residues on this guy, and miraculously it's positive. Every single residue is absolutely positive. Amazing. You say, okay, I don't know how this person came up with it, but surely it's easy now. Now that I have these gammas, it's easy. Now I'm going to go add all these other things to it. No, everything else doesn't work again. Only this thing works. Nothing else works in its neighborhood, right? Now, when you run into a miracle like this, you can't, nothing's a miracle. So you study where this formula comes from, and eventually you realize that this formula arises from the picture where you replace little point particles by imagining they're loops of string. Okay, so that's where string theory really came from. It wasn't just the idea that, oh, let's say today that things look like little loops of string, and tomorrow we'll say they look like snowflakes or some other shapes, okay? So it does something, it accomplishes something. In fact, in the 50 years that people have thought about this problem, no one has come up with another formula, okay? There is no second formula which has this miraculous property. So that's why people take string theory so seriously. And if someone else comes along and tells you they have a whiz-bang theory of quantum gravity, you say, so what's your formula? And you'll find they very quickly change the subject, or start talking about philosophy or sociology or good and evil, right? Say, okay, but your formula again, what is it? So, in fact, I think this is something not for the infinite future of the 21st century, but it's something I think some smart high school or college student, probably somewhere here in India, maybe someone in the room, can actually figure out. I think this is a very accessible challenge to prove that this formula is unique. And actually, it's very interesting because you can show that the reason why these dumb attempts with polynomial over polynomial, the reason they fail, when you study it, it's a very simple reason. I don't have time to explain it, but you find that these simple things fail precisely because gravity is a long-range force. Okay? In fact, there's nothing to do with fancy things like diffeomorphism, invariance. In any theory where there's a long-range force, you would have an analogous issue. So it's just that we run into it and notice it for gravity in 4 dimensions. But if we're doing Yang-Mills in 5 dimensions, phi-cube theory in 7 dimensions, in any theory where there's a long-range force, these idiot things, which are just modifying with polynomials, don't work. And you need something with these gamma functions in it. You need something stringy. Okay, so I haven't had time to pose it in this talk sharply mathematically, but if there's a smart high school student, or certainly an undergraduate, who wants a good problem to rocket them to fame and glory very quickly, it's a completely well-posed mathematical question whether string theory is the unique, essentially unique answer to this problem. Okay? I suspect it is. And that, in fact, if one could come up with it, so there's an extraordinarily simple identity that you have to prove for this positivity, even for the ordinary string theory answer. And it's remarkable. It's a very simple identity to state. You can stare at it for months, as I have, and try to prove it in other ways. So far, the only way we know how to prove it is to bring in all the machinery of thinking about strings and the world sheet and all the rest of it. But if there is another way of understanding it or proving it, it's very likely related to some new way of thinking about what string theory itself is, where the concept of the world sheet is much, much less important. I think there's many reasons and points of view that make this a likely thing to happen. But in any case, I think it's a very accessible and concrete challenge. All right, but of course, thinking about scattering amplitudes in flat space in the weak coupling limit is how string theory was born. As you heard in the past number of talks in the last 20 years, it's become clear there's a huge number of other playgrounds in which stringy ideas are relevant. There's amazing equality and correspondence between string theory, particle physics, the idea of holography. This is all beautiful and very important, but it's also important to point out that our world is different than these toy models that we understand in an extremely fundamental way, which goes to the heart, really, of what's so difficult about the idea of emergent spacetime. It's the time part of emergent spacetime that's really extremely difficult to think about what it might mean. This picture of the world as a tin can, or an empty de Sitter space inside, is eternal. It goes in the past and the future. And the time that flows out on the boundary is the same as the time that flows in the interior. But our world is not like that. We had a cosmology. There's a Big Bang singularity somewhere in our past. The whole notion of time is likely breaking down there. And even more disturbingly in many ways today, we have a universe that's accelerating. Because it's accelerating, for the first time, I think ever, in our history in physics, we're forced to confront finiteness of a fundamental sort. We have access to only a finite number of degrees of freedom in an accelerating universe, because all the imagined infinite part of the universe outside our cosmological horizon is being inflated away from us more quickly than light can get to us. So we really have access to a finite amount of stuff, and that means that all of what's normally necessary, especially in quantum mechanics, to precisely talk about observables, a separation of the world into an infinite observer and a finite system that's being studied, that's now impossible. Cosmology makes that impossible. And this is, I think, a truly big, deep conceptual challenge. It's going to force us into thinking about what emergent space-time might be, with an emphasis on the time part, and perhaps even an extension of quantum mechanics to help us figure out what we're allowed to talk about in universes like this. All right, so that's a summary of what the theoretical challenges are as they're handed to us. And now, if I can just take 5 minutes, I want to tell you about. I probably won't tell you why cosmology is number theory, but at least tell you some of the speculations. So, and perhaps I think this is the most concrete speculation, is that what we'll find is that space-time and quantum mechanics have to emerge hand in hand from something else. And this is slightly more radical than what most people, and there's less evidence for it at the same time, but it's I think a slightly more radical than what most people have been talking about, or what most people imagine. Most people imagine some picture. Most people imagine that we've taken a lesson from holography, that quantum field theory is king, that we have a definition of the physics given by a theory that lives on the boundary, and gravity is somehow emergent on the inside. And nothing wrong with that picture. In the case of anti-de Sitter space, it's perfectly true. Of course, again, our world doesn't look like that, and the fact that the time is the same on the outside and on the inside is a big part of why it was possible to discover this kind of relationship to begin with. You know, dualities are spectacular things, but in the end, they don't force you to invent anything fundamentally new or discover anything fundamentally new. You're finding equivalences between objects that existed ahead of time, and finding amazing relationships between them. But the difficulty with emergent time is that we need some new language in order to describe physics without time. Okay? But anyway, that's, I'm getting to that in a bit. Of course, most people have the attitude that we've learned that quantum field theory is king, quantum mechanics is king, and so we're just going to learn how space or space-time emerge out of quantum mechanics. So quantum mechanics won't be touched, and we'll get space coming out of it. Now, in the context of holography, we keep having to remind ourselves that space, not space-time, it's space which is emergent. Of course, this is still an amazing thing. Space is emergent, gravity is emergent, and in the past number of years, there are remarkable connections emerging between not just some random strong dynamics of quantum field theory, but perhaps quantum entanglement as the fundamentally new aspect of quantum mechanical life, having to do with the emergence of a geometry. So this is almost certainly, it's very beautiful, it's almost certainly connected to the way space emerges in the standard gauge gravity dualities. But what about time? Again, as I've said, it's a much taller order, and I have no idea how to go about approaching this question directly. But I take some inspiration from the fact that sometimes in the past, big clues are hiding in plain sight as some funny features of a standard existing theoretical framework. And in this case, at least one small hint or clue towards what emergent time might be about, you can maybe look for by thinking, saying that time is emergent or space-time is emergent is such a huge thing that it seems to me very unlikely that it's going to have to change the way we think about things in at least as big a way as replacing classical phase space by Hilbert space changed the way we think about ordinary dynamics. Okay? And so, therefore, it's possible that there's a clue for how to think about that by trying to think about completely ordinary physical processes, ones that we normally understand by thinking in terms of quantum evolution through space-time, whether we can understand those things without using quantum evolution in space-time, but some other way. Okay? And perhaps that'll tell us some way of thinking about what emergent space-time might be. And if we go back to the LHC, where in order to extract predictions for signals for supersymmetry or all sorts of other exciting physics, experimentalists have to beat down humongous backgrounds that are millions of times bigger than the signals that you're looking for. So here a very practical problem, very removed from all the highfalutin philosophy that we just talked about, rears its head, which is how do you actually calculate the cross-section, the amplitude for 2 gluons coming in and 4 gluons going out. Okay, that's a big background to supersymmetry searches at the LHC. And this is the boring, gucky physics in principle. Nothing exciting going on here, right? Some guys just got to sit down and do this grungy calculation, and we have a chauvinism in at least our part of theoretical physics that we define as interesting those questions whose answers are simple. And those questions that just look complicated, we said, well, that's someone else's job. Okay, that's not fundamental physics. But of course, physics is the wonderful way of rewarding morally good behavior. And the people who did these calculations found something amazing. If you use Feynman diagrams, this is, 200 pages of algebra. There's no reason to suspect it looks simple. In fact, here's a simpler process is what you get using Feynman diagrams. Just 2 to 3 gluons. It's like 30 pages that looks like that if you just open up the textbook. But people discovered in the late 1980s that the final answer could be written on a single line. Okay? So we now know that this is a tip of a very big iceberg. The standard way of doing physics, using this simple physics, using Feynman diagrams, makes the rules of space-time and quantum mechanics manifest, but it's obviously hiding some extraordinary new structures that allow the final answer to come out to look so simple. So here's a playground where you can see maybe there's some other way of thinking about what these things are that might give us some insight. Well, where we see the space-time and quantum mechanics go out, because if you put them in, you get 100, 200 pages of algebra in order to make it clear that they're compatible with each other. Now, here's a very beautiful fact that if someone just hands you the final answer, said, here, I did it, I summed up the 200 pages of Feynman diagrams, you can check whether they're right or wrong without doing the exercise yourself. Because the fact that the answer is local and that it's unitary is encoded in a very simple and beautiful way in the singularities of the final functions. So the analytic structure, the singularities of the final functions tell you about locality and unitarity. And here's already one beautiful fact which makes it strongly suggest that these two ideas are linked to each other, is that in fact, it's one and the same thing. Locality tells you where the poles and the amplitude are, and unitarity tells you what the residues are on the poles. They're not two radically different parts of the thing. There's one function and one natural question you can ask about it. Half of the question is about locality. The other half of the question is about unitarity. Okay? And pursuing this has led to in the past number of years to a remarkable confluence of ideas between string theory, twistor theory, spin chains, and new structures in combinatorics and algebraic geometry that now, for some special simple theories, planar supersymmetric, maximally supersymmetric theories in the planar limit, in 4 dimensions at least, do give us a complete formulation of the physics where you make no mention of space-time or quantum mechanics or Hilbert space or anything else, but you get the final answer. So if you want to calculate, now this is not for some, this is literally for this process at the LHC, gluons of these helicities, okay? You need it. It's part of some standard backgrounds at the LHC. You could use hundreds of pages of Feynman diagrams, or you could draw this picture in an auxiliary space, okay? I'm not telling you the rules for how to draw the picture, but there is something that is no space-time, that is all about objects that live in Grassmannians, closely related to projective geometry, positivity, and so on. And the volume of this thing is the scattering amplitude. And all of the properties, the fact that it's local and unitary together, emerge as a consequence of this underlying combinatorial geometry. Now, that's just one example that I happen to be familiar with because I've been working on it, but there's many other threads of this type. I'll just mention 2 of them before ending. These are qualitative things, but which I think suggest that space-time and quantum mechanics are going to come out together. One of them is that it's a curious fact that all the best ways we have of thinking about quantum field theory in 3 + 1 dimensions ultimately live in another space. So we're used to defining quantum field theory in Euclidean space, for example. Or more recently, we're starting to find structures that are obvious when we think about it in the maximally relativistic signature with 2 spaces and 2 times. This is, I think, extremely interesting because in neither one of these pictures is there any locality or is there any unitarity or causality. It's only the analytic continuation that makes it simultaneously causal and probabilistic at the same time. So once again, causality and unitarity, the notion of time evolution and probability are closely tied together. They're inevitably tied to each other. A more qualitative fact that everyone has run into in one way or the other is that while it's very strange that relative space-time and quantum mechanics on the surface fight each other in trying to be described in a common framework, which is why we have to introduce this very rigid framework of quantum field theory to talk about them at the same time. Behind the scenes, they buttress each other, and they make each other more rigid and robust. After all, if we didn't have special relativity, quantum mechanics might have been some stupid local hidden variables theory, okay? But it's relativity that makes it impossible. Simultaneously, if we didn't have quantum mechanics, relativity may have been a dumb emergent symmetry at long distances. It really might have been an ether, okay? And relativity would have been a long-distance emergent property. But it's quantum fluctuations that imprint information from short scales all the way down to longer scales that makes that impossible. So these ideas fight on the surface, but are best friends behind the scenes. And that also makes it seem that they're going to emerge together. All right, so that's all. So I'm going to ignore all of that. And just to say, back to Earth, we have a full plate, even on the 10-year time scale, both for the center, of course, as well as for physics. It's a critical era for experiments in the LHC, cosmology, and also dark matter that said nothing about. Of course, theorists will continue to explore the marvelous theoretical structures at our feet. We should keep asking this question, what is quantum field theory, till we get a good answer. And I think we should further expose in a center like this, which combines theorists of all stripes together, in one spot will make it even easier to further expose this amazing unity between physical and mathematical truth. Thank you very much.